对啊，有看到，好。Okay, everyone, let's get started. Do we have a question from last time? Let's go over a very quick review of last time. So basically, last time we defined this abstract meaning of vector space. So it's a generalization of those 2 and 3 and n-dimensional real space we have. And but now we have abstract definition of vector space. It's just an arbitrary set with some addition and scalar multiplication rule. And vector space need to satisfy 10 rules. So they need to satisfy 2 closure rule under addition and scalar multiplication. And there are those 8 axioms about their addition and scalar multiplication need to satisfy additionally. Okay. And then we we give a little taste of abstract algebra. So this is what you do in mathematical algebra. Is you start with these very abstract rules and try to derive more rules. And in particular, we have seen 4 rules. So we think that the 0 element and the minus elements are unique, and also scalar 0 times any vector into vector 0, and minus 1 times scalar minus 1 times any vector equal to this inverse vector inverse minus x. Okay. So this is a quick review of this abstract vector space, and now we are going to study properties of those vector spaces. And the first property we are going to talk about today is a subspace. Yeah. So what is subspace? We have an example of a subspace in R2. So let's think about R2. There are those set of real vectors. And now we think about a subset of R2 that's just every vector in R2 with the first coefficient being twice the second coefficient. So x1 equal to second coefficient being twice the first coefficient, so x2 being twice the x1. So you can write it as some number c as x1 and twice c on x2. And so everything of this is element of S. And we see that if you do scalar multiplication on this thing, it's also inside S. So alpha times x is this alpha c and 2 alpha c. So it's also inside S. And we can check both of the closure of vector space. So anything from S, if we do scalar multiplication and addition, they are still inside S. Okay. So here is a check of the second rule. So a and 2a and b and 2b, we do addition on them, is a plus b twice a plus b, so it's still inside S. Okay. And then we see that this subspace, this subset of R2 is also a vector space itself, because it satisfies the closure rule, and we need to check a little more. And then we also check those those 8 rules. We'll see that those 8 rules are also satisfied on this subspace S in particular. So there are two rules that are harder to check. So there are rule A3 and there are rule A4. So you need to check that the zero vector and the inverse of everything inside S is also inside S. And they can be used, but they can be derived easily from our theorem 3.1.1 because we can just multiply 0 with x, and we know it's the zero vector is inside S because we just say any scalar multiplication is still inside S. And then similarly, minus 1x, this minus x will be inside. So minus 1x will be inside S, so minus x will also be inside S. Okay? And then other rules are just follow directly from those rules. This commutative, this addition is commutative. So this was true inside the big space V, and this is also true inside the smaller space S. Okay. Okay, so that's proof that our S is space is a vector space itself. So the number of elements is a subset of R2, and the operation are the same. And if you take this set and this addition and the scalar multiplication, we see that it's still a subspace. It's still a vector space itself. And here we have a definition of a subspace. So S is a non-empty subset of vector space V if you only need to satisfy two things. So first, it need to be closed under scalar multiplication. So every alpha x, every alpha x is still inside S if your x is inside S. And similarly, if x and y is inside S, then it still is closed under addition. So x plus y is still inside your S. Okay. And here, I guess you need to stress one more time. So if S is a subspace of V, and V already has a scalar multiplication and addition, then we need to pick the same scalar multiplication and the same addition rule for S. So you cannot change those two things here. Okay. So this is a bit different from chapter 3.1. Chapter 3.1, we say that we have a set of V, we can pick whatever scalar multiplication and addition we like for V to make it into a vector space. Okay? And but once you fix your scalar multiplication and addition for V, then then the scalar multiplication and addition for a subspace of V need to be the same scalar multiplication and addition. Okay? And anyway, then S is called a subspace of V. And yeah, so this whole section is talking about subspace. Okay. Any question about definition? And also, as we just proved before, so here we just give a definition here, and we kind of prove here, not quite a theorem, but we see that if the subspace satisfies this closure rule, then it will satisfy also the 8 other ACNs on its addition and scalar multiplication. So it's really a space itself. Okay, and yeah. Subspace is closed under the operations of V, as we said, and the theorem we didn't write down a full proof, but we see the ideal proof is that every subspace is a vector space, and and there are two subspaces that are special that because every vector space has those two subspaces. First one is the zero subspace. So the subspace where you only have a zero vector, and well, you do everything to it, it still go back to a zero vector, and it's quite boring, but it's a subspace. And another subspace is just well, you pick everything. So everything is the set of everything is a subset of your full set. Okay, and because V is a vector space itself, obviously, well, you pick V as a space, it's still a space. It's still a vector space. Okay, so those two are the trivial, I guess not quite trivial, but the easiest subspace. Okay, and I guess they are non-proper subspace. And then the other subspace are called proper subspace. So and this 0, the subspace of only 0 vector is called the 0 subspace. So this is just some notation here. Okay. And lastly, some example of subspace. We see an example of R2, then let's see an example in bigger subspace in R3. So we have the set of vector that is, so vector in R3 has a form x1, x2, x3, and now we constrain it to x1 equal to x2. Okay? So it's a vector of form is AAB, and first we check, so we only need to check the two closure. So we check the first closure, so we have alpha times this AAB, then we have alpha A, alpha A, and alpha B. So we see the first two coefficients are still the same, so it's inside S. And similarly, we check C2, so AAB plus CCD, then we have this A plus C and A plus C here, they are the same. So we see still inside S. So S is the subspace of R3. Okay. And then we see an example where we actually not a subspace. So S is this X and 1. So we have the second coefficient fixed to be 1. And we want to see whether this is a subspace. And then we check rule from number 1. So some arbitrary alpha times X times 1. Then we see the X and 1. And we see the second coefficient become alpha. So if alpha not don't equal to 1, then the second coefficient become not equal to 1, then this is not S. So just from checking C1, we see that, well, this X and 1 is not closed under scalar multiplication, so it's not subspace. And we check C2, we see that it also doesn't satisfy. So x1 and y1 adding together, then we have x plus y and 2 here, so this is not a subspace. Okay, any question? Yeah, then we have another example, and it's a bit more complicated. So now we think about our parent space is this R2 by 2, so the set of 2 by 2 matrices. So it has 4 elements, and we say if the off diagonal elements are inverse to each other. So A1 2 equal to minus A2 1. Okay. And so A will, so any matrix inside S will be in this form. So A, B minus B and C. So you see this thing is a negation of this thing, and all other things are arbitrary. And yeah, so once again we check scalar multiplication and addition. So scalar multiplication, those two are still arbitrary, and we have alpha B and minus alpha B. So they are still negation of each other. So this scalar multiplication check out. Then we have addition, so we have AB minus BC and DE minus EF, and we add them together, then we see this is B plus E here and minus B plus E here, and yeah, they are still different by a minus sign, so C2 also check out, and S is a subspace of R2 by 2. Okay, so here are some examples of subspace. I think this is quite straightforward. You give some subset, and sometimes they are given as rules, and you just check the scalar multiplication and addition. You see that whether both of them check out, whether S is closed under scalar multiplication and addition, and then you will see whether S is a subspace of your parent vector space V. Okay, so this is the idea of subspace. Okay. And now with this idea, now we talk about a very important subspace. Okay, so this is a concept will be used throughout the course. It's a normal subspace of a matrix, and it has well, later on we'll see it has a strong relation to this. Well, I guess here we already see. So we use this idea of subspace to talk back to something about solving linear system. After all, a big part of this course is talking about solving linear system. Okay, so we have this A B equal to n by n matrix, and there is going to be some linear system associated with A. And the linear system we are thinking about is this A is equal to B. So this homogeneous system, just want to see is there some set of X such that A times X equal to 0. And we know that there is always a trivial solution. there is always a trivial solution of x all equal to 0, but sometimes there are other non-trivial solutions, and we want to see about what are the set of all solutions to this homogeneous system. And it turns out it will be linear space, and it will be called null space of A. Yeah. And so this null space of A will be a subspace of Rn. So A is, so let's check the dimension a little bit here. So A is n by n matrix, so there are n rows here and n column here. And x will be a column vector of length n. Okay. And so every x will be a vector inside Rn because well they have length n. And we know 0 is always this 0 vector is always a solution here, but we want to see whether there are more solutions. And so this is the definition: n of A equal to set of x such that Ax equal to 0, and this is called the null space of A. And it's a null space of A, and it is a subspace of Rn. And let's check that it's actually a subspace of Rn. And we need to check C1 and C2. So C1 says that if something is in the null space of A, and you multiply it with a scalar alpha, then it's still inside the null space of A. And well, null space is defined with this rule, and let's just play it out. So we have A times alpha x, and we want it to be a 0 vector. And now we just use a rule on matrix multiplication. We can take out this alpha, and so this is alpha times ax, and and because then we have alpha x equals 0, so this is alpha times 0, and we know. I guess we didn't quite prove that alpha times 0 is 0, so that's being a little pedantic here and prove alpha times 0 equals 0. This can be do going from, let's see, let's go from here to here. I think it is easier. So, and I'll write 0 vector. So 0 vector we know from 3.1.1, we know this is 0 times 0 vector. Then 0 times 0 vector then is equal to, I guess it's also in one of the exercise problem, but we didn't put it as homework. Anyway, then 0 equal to alpha times 0, so both of the number, and every number times 0 is 0, and alpha times 0 and 0 vector, okay, and then we can have alpha times let's do this very slow, 0 times 0 vector, okay, and so this is equal to, but then we back to 0 times 0 vector equal to 0 vector, okay, so this back to 0 vector. So basically we take out 0, and we have 0 equal to alpha times 0 to get our alpha out. And so every alpha times 0 vector equal to 0 vector. Yep. And I guess this is also in Rn, so it's easier. We don't need to really do this, but anyway, it's nice to know that this is true for any vector space. But in Rn, you can just know that the 0 vector is in Rn, 0 vector is just a vector where all elements are 0. So you times alpha, then every element got multiplied by alpha is still 0. And back to our null space being a subspace of Rn, and we see that A times alpha x equal to 0 vector. So we know alpha x is by definition also inside the null space. Okay. And similarly, we have x inside null space, y inside null space. So we have ax equal to 0 and ay equal to 0. Then we just add together those two equations. So we have ax 0 here and ay 0 here. This is by definition. Then then we add them together. Then on the left-hand side, we can have this distributive rule on matrix multiplication. So this is a of x plus y, And on the other side, we have the definition of 0, so 0 plus 0 equal to 0. So then we see that a of x plus y also equal to 0, so x plus y equal to, x plus y is inside null space of A. Okay. So yeah, we have the closure under both closure C1 and C2. Then we have this null space is a subspace of R. Okay. And yeah, I guess we do this to save a lot of headache. So because it's a subspace, so then it's a vector space automatically. So if you want to check what I mean is that if we check whether this is a vector space directly, then you also need to check A1 to A8. But because we know it's a subset from Rn, and Rn is already a vector space, so only need to check C1 and C2 to know that N of A is also a vector space. Okay, so that's a bit nicer. And yeah, then now we start doing calculation on null space of a whole bunch of matrix. And as we said, this is an important part of the course. And yeah, you are going to do this a lot of time. And how we do this is it's a kind of the other way around. So we define this null space as all solution to this thing, and so this is what I mean is that we have this definition, but we are not going to calculate this thing to find all solution of a homogeneous subspace, homogeneous system. Okay. And so what we do is we already know how to find the solutions of a homogeneous system, and we use it to find our null space. Okay. And how we do this is we go back to our favorite Gauss-Jordan reduction. Okay. So yeah, most of the calculation we do here is Gauss-Jordan reduction, and we turn things into RREF. So we do Gauss-Jordan reduction to this Ax equal to 0. So we take our favorite augmenting matrix. So we have A here and 0 here, and we Gauss-Jordan reduction on this part. Okay, and yeah, so we see that we make our pivot row, and we make this 0, and then we make this pivot 1 here, and then we subtract up here, then we make this 0. So let's mark the important place here. So we want to make this 0, this 1, and this 0. Okay, and with our Gauss-Jordan reduction, we get our REF. And so we have this equation equal to 0, and this equation equal to 0. You write it all is like those. Okay. And anyway, so we analyze this, and we see that we know we have a 2 lead variable x1 and x2 here, and 2 free variable x3 and x4 here. And as we say the free variable as free, and the lead variable expressed as the free variables. So if x1 equal to x3 minus x4, and x2 equal to minus 2 x3 plus x4, and we change the name of x3 and x4 just because, just maybe easier handwriting. Okay, and yeah, so we have 2 variable alpha and beta here, and our solution are those things. Okay, so they are these alpha minus beta minus 2 alpha plus beta and alpha and beta. And here, but here we see an interesting concept here. So this subspace, we see that it can be always written in an interesting form. So it's written as what is some function of alpha and beta, but then we can separate out to this thing into a part that's a vector that only depends on alpha, and a vector that only depends on beta. Okay. So yeah, so you look at this thing, you see this is alpha vector, so alpha minus 2 alpha and alpha 0. Then the beta vector minus beta, and beta 0 minus 0 and the beta vector. And even more, so this vector is proportional to alpha, so you can write it as alpha times a vector. And similarly, this is a vector times beta. So this is beta times another vector. Okay. And so this form is actually very important. We're going to talk about this a lot more today. Okay, so this is a form of some scalar plus a vector, scalar times a vector plus another scalar times another vector. Okay, and so we see that this subspace can be written in this form, and actually later on we're going to see every subspace can be written as this form. Okay, or any vector space can be written in this form. So some coefficient has another vector, some coefficient has another vector, and well, if it's a more general subspace, then you are going to add more terms. Okay, but anyway, back to our null space, we see that the null space is this form. This well, solution has a solution to x equals 0 has this form, and the null space is this form. Okay, yeah. So this is the important part. So we see the null space of A is a vector of this form, and yeah, let's talk about vector space of this form. Okay, and this is so important. It actually has a name. So this is called the span of a set of vectors. Okay, so the vectors here. So here the alpha and beta are arbitrary scalars. So the important thing is we have two vectors here. Two vectors here, and we see that the null space of A is determined by this vector minus 1, 1 minus 2, 1, 0, and this vector minus 1, 1, 0, 1. And we see that in general we can always define, we have a set of vectors, then we can define the vector space from that, and we just define the vector space as I guess we need to, so this definition always define the subspace, because those V1, the V2, and the Vn, they all need to already from a vector space V. And so there is already scalar multiplication and addition on those V's. Okay, and anyway, so this span of vector is a set. Okay, and yeah. I guess I should emphasize here. So the span is the span is a set of vectors of this form. So alpha v1 plus alpha v2 and all the way to alpha vn. Okay, so this thing set of vector of this form is called a span of v1 and vn. And the vector of this form is so important. It also has a name. It's called a linear combination of v1, v2 to vn. So we just pick whatever alpha 1 to alpha n, and multiply them with v1 to vn and adding them together, and it's called a linear combination. And I guess a bit of motivation of this name. So remember, linear means that you do two operations. Linear is scalar multiplication, scalar mod, and addition. Let's write this a bit better. So linear means two things: scalar multiplication and addition. And you see this linear combination is exactly you do those two things on your vectors. So you have a scalar multiplication on your vectors, then do addition on them. Okay. So yeah, it makes sense that you have a linear combination, so you do linear operation to combine them. Okay. So scalar multiplication and addition on your vectors, then it becomes a vector. Okay, because well, the vector space is closed. So you do this thing, you still get a vector inside your vector space. Okay. And so this is a linear combination of vector, and the set of all possible linear combinations. So the set of those things with all possible alpha and beta. So I guess I can write a little more. So all here means all alpha 1, alpha 2 to alpha n. Okay. So you go through all possible alpha 1 to alpha n, and collect them together, and you get a set, and the last set is called a span. Okay. Any question? And yeah, so we see that in our example, our null space, this n of A, is is the span of 1 minus 2 1 0 and minus 1 1 0 1. Okay. Here is the idea example of span. Okay. And let's see more example of span. Okay. So and this is another example where span is a proper subspace. So we back to R3. Okay, and we can have a span of E1 and E2, where E1 and E2 are this standard vector 1 0 0 and 0 1 0. Okay, and span will be vector of this form: alpha times 1 0 0 plus beta times 0 1 0. This is just by definition we have alpha E1 plus beta E2, and this will be alpha beta 0. Okay. And then we see that the span is well, just everything inside this x1 x2 plane. Okay, so the third coordinate is 0. Okay, and we can have a geometric interpretation of this subspace here. Okay, so we see that we have our vector space is our R3. So x1, x2, x3 have this three-dimensional space. No, I guess. Technically, you cannot say three-dimensional because the dimension we haven't defined. But anyway, so we have this R3. I guess we can define the number of dimensions for R. It's just n. Okay. So we have this R3 here, and then the subspace is basically R2 here. So it's a space spanned by E1 and E2, and it's just this plane here. So everything inside this plane, say for example this x, is inside our subspace span E1, E2. Okay. And yeah, you can check that span of E1, E2 is actually a subspace. Okay. And also we can have a span of more vectors. So you have a span of E1, E2, and E3. Then you will be vector of form alpha, beta, gamma, and you see that this is just all possible vector in R3. So yeah, and so this span is just the whole space. Okay. Okay. And yeah. Okay, so this is two subspace of R3. So span of E1, E2 is this plane, and the span of E1, E2 is E3. Then is everything. Okay, and yeah, then we here prove a theorem. So I guess we kind of say this a little bit already, but let's actually prove this as a theorem. So if you just have so we start with a vector space V and have pick a whole bunch of vectors inside, and take the span of those vectors, and it will always become a subspace of V. Okay, so span subspaces. And the proof is quite straightforward. You need to prove, to prove something a subspace, you need to prove closure under scalar multiplication and closure under addition. So yeah, so let's check C1, C2. C1, so we have some vector, any vector inside this span, and we know by the definition is this linear combination. So this is alpha 1 to alpha n linear combination. And we do a scalar multiplication on it. And so then, by distributive rule, you can distribute this beta on every of this linear component. So it will become beta alpha 1, beta alpha 1, beta alpha 2, all the way to beta alpha n on Vn. And but it's beta times alpha 1, beta times alpha 2, beta times alpha n. Those are still scalars, and we call them gamma 1, gamma 2 to gamma n, but all those are scalars, so this satisfies the form of linear combination of V1 to Vn, and yeah, so this is inside span of V1 to Vn, so we see that beta times V is inside span. So here, important thing is, I guess, scalar multiplication is closed. So scalar multiplication still give you a scalar. So any two scalar multiplying together still give you a scalar. So beta multiplying on every scalar is still a scalar. Okay. And yeah, so then we check C2. Now we need to have two vectors. So let's say we have a v vector with coefficients alpha and alphas, and w vector with coefficients betas, and then we do addition on that. Okay, so v times v plus w, and once again with the distributed rule, so this will be alpha 1 plus beta 1 times v1 plus alpha 2 times beta 2 times v2, etc. And once again, scalars are closed on the addition, so any scalar alpha plus any scalar beta is still a scalar. And so we see that this is still satisfy the definition of a span, and so we see addition is still inside the span, so span is closed under both C2 and C1, and yeah, it's a subspace of V. It's quite straightforward. Okay, and yeah, so this is a proof where every span of any set of vectors is a vector space. Okay, and yeah, now let's go back to seeing a bit more about geometric property of a span. Okay, so let's say we go back to R3, so it's easier to visualize. Okay. So if we have x, y being two vectors in R3, and we can think about their span. Okay. So if they are not, x and y are not collinear, then the 3 point, the origin 0, 0, 0, and the point of x, so x1, x2, x3, and point of y, y1, y2, y3. And if x, y not collinear, then those three are not on the same line, and you have 3 points, you can define a plane. Okay. And then we see that the plane defined by xy will be the plane. So I guess the plane determined by xy. So the plane where defined by those 3 points will be exactly the span of x and y. So you have any z equal to some c1x plus c2y. Then that z will be placed on this plane that's determined by the 3 points. So let's see this in picture. So we have, I guess I should mark the 3 points here. Okay. The 3 points, this x point, this y point, and this 0 point. Well, if they are not collinear, they have a triangle kind of here, and the triangle is on plane, and we extend this triangle, you get a whole plane. And then we say any span. The span is just this whole plane. So for example, we have some z, that's c1 times x, and plus some c2 times y. And yeah, then you see that z is can be written as the c1x plus c2y, but c1x is on this plane, and the c2y is on this plane. The integral is still on this plane. Okay. So yeah, here is a bit of a geometric interpretation, and proof that span of xy is just the plane where both the x vector and the y vector is on. Okay, and yeah, so this is span of xy when xy are not collinear is the plane in R3. Okay, anyway, any question? Yeah, and let's keep going. Okay, so far we talk about definition of span. So we kind of go from a set of vectors. So we have a whole bunch of vectors, and then we can go to span, which is a subspace. Okay. This is a definition of span, and then we go the other way around. Okay, and then we now think about if we have a subspace, then we find the vectors that span that. Okay, so now we go from subspace and want to find a set of vectors. Okay, so this is what we do now, and it's called spanning set of vector space. Okay, so yeah. Yeah, so we have, as we said, I guess I should return those here. So here, so far we have vectors, and go to subspace. Okay. And then we can think about another thing. We can think about we have subspace subspace, and where we can find a set of vectors that will span our subspace. Okay. Okay, and yeah. And so if we have this thing, then we have well, first we have two nets. Okay. Yeah, and so if the span of those vectors equal to your subspace, then first wording we have is this subspace. If we call it to make this wording a little less dumb, let's call this space W. You can say some space W is spanned by these vectors v1 to vn. Okay, and also this set of vector v1 to vn. We can call it a spanning set for V. Okay. Yeah, so here we just have three names for this relationship between set of vector and the space spanned by them. So first is we say the set of vectors span the vector space. Oh, here I guess I should not have V here, because we already have a parent space being V. Okay, so let's call this W, and this W, and this should be W to avoid confusion. Okay, so we have the parent vector space being V and the subspace W. Okay, and if W equal to, so if so here I guess I should write this. If W equal to span V1 to Vn, then there are three ways we to describe this. Okay, so we can say V1 to Vn span W, and or we can say W is spanned by V1 to Vn, and or we can say V1 to Vn is a spanning set for W. Okay, so we can say V. So there are three wording here. So E span W, or just a passive passive tense of this. So we can also say W spanned by V, and also V spanning set. Okay, so three wording, and anyway, so so here we have a definition. We have a definition that a set of vector V is a spanning set for I guess to make it consistent. So let's write here W again, W, to avoid a bit of confusion. Say a set of vector V is a spanning set for W if only if every vector can be written as a linear combination of V1 to Vn. Okay, so here's the definition. And I guess yeah, so so by looking at the definition, it might be it might look a little redundant, because we already say we already define how a set can be spanned by a whole bunch of vectors, right? And I guess let's do a little bit of a distinction. Okay, so before we have the definition where we define a span of a set of vectors. So from a set of vectors, you can find a span is a set of all linear combination. Okay, and as we said, this is from a set of vectors, you can find a subspace. It's just this span. Okay, and by this definition, the spanning set is a little bit different. So this is the other way around. So as we said, this is from W, we find a set of vectors. Okay, so from this definition is W, we can find is a spinning set. So it's a V1 to Vn. And I guess here the important thing, so make this less trivial, is that the spanning set is not unique. Okay, so spanning set not unique. And this is different from the other thing we just have. Okay, so you might have V1 to Vn or W1 to Wn. So okay, so you can have a different spanning set for subspace. Okay, and yeah, as we said, this is different from the definition of span. Span is just a function. It's a one-to-one. It's I guess not one-to-one. It's called yeah, it's a function. So you have a set of vector. You can find it's a unique span. But for unique span, it is a unique span vector subspace. But subspace, you can find many different span. Okay, and actually, this is the finding different span is something that we'll study basically the rest of this chapter. How do you find the base set of vector to span your subspace? Okay. And yeah, let's see an example to see whether some set of vectors span our R3. Okay. And I guess here is something that we can get a little interactive. We are short in time, but let's see, try to do a bit of that. Okay, so yeah, we have a whole bunch of vectors, and they want to see whether they are spanning set of R3. And I guess here the subspace is the whole space. Okay. So we have a whole bunch of vectors in R3 and want to see whether they span the whole R3. Okay, and the first one I think is a bit easier. So we have the set being E1, E2, E3, and 1, 2, 3. Okay, and let's take some votes. So if you think this set of vectors span R3, raise your hand. Anyone? Okay, 1 vote, 2 votes. And if you think it doesn't span R3, raise your hand. Does it? Oh, we also have 2 votes, so we're 50-50. Okay, let's see whether this span R3. Okay, and so we want to see whether every vector of R3 can be written as a linear combination of those vectors. Okay, so this is the definition. Yeah. Yeah, I guess here I can write only if, because anyway, yeah, because this is a definition. Definition I should only write if, sorry. Okay, and yeah, let's see how this works. And there is indeed a spanning set, and actually this is more than enough. So only the first 3 vectors are. Only using the first 3 vectors is enough to span R3 because you have all the standard bases. You have 1, 2, 3. This 1, 1, 1 here, and any vector ABC inside R3 can be written as A times 1, 0, 0 plus B times 0, 1, 0 times C times 0, 0, 1. This is just ABC. Okay, and this is just A1 times B2 times E. C3, and then this extra 1, 2, 3 here, you can just multiply it with 0, so don't interfere with us. Okay, so we see that A is a spanning set of R3 because everything in R3, this ABC, can be written as AE1 plus BE2 plus E3, and then 0 plus this extra vector 1, 2, 3. Okay, and yeah, then we can go slowly, so let's go to next example. I think this can still be done by eyes. Okay, so second example B is this spanning set. So if you think it is a spanning set, raise your hand. Now we have more hands. Okay, and if you think it is another spanning set, raise your hand. Okay, so we have okay. So now we have an overwhelming vote that this is a spanning set. Okay, and indeed this is a spanning set. Oh, here, sorry, missed a note. So this is called a standard spanning set, kind of. Okay, yeah, the standard then we'll have we'll talk about this a little more, bit more later. Okay, and yeah, let's talk about B. And so we have ABC, and we want it to be some alpha 1 times is 111, some alpha 2 times is 11, and some alpha 3 times is 100. And let's just write down this as well, linear equations. So we have those three vectors together, adding together will be alpha 1 plus alpha 2 plus alpha 3 on first coefficient, alpha 1 plus alpha 2 here, alpha 1 here. And then we can write all this as actually go back to a linear system of equations. So this will be alpha 1 plus alpha 2 plus alpha 3 equal to A, alpha 1 plus alpha 2 equal to B, and alpha 1 equal to C. And we can solve those linear equations. So they are in nice form. We can do back substitution. So we see alpha 1 equal to C. And then because alpha 1 equal to C, then alpha 2 will equal to B minus C. And alpha 3 equal to this A minus alpha 1 minus alpha 2. So, oh, yeah. Yeah. A minus alpha 1 minus alpha 2, which equal to A minus this B. So, this is A minus B. Okay. So, yeah, so we see that for every ABC, we can always solve for alpha 1, alpha 2, alpha 3. And indeed, and it's also a unique solution here. And yeah, let's check it. So alpha 1 ABC, you can always write it as is C times 111, B minus C times 110, A minus B times 100. And you add them together, you see our solving linear system works out. And yeah, it's ABC. So B is also a spanning set. And yeah, I guess we can put our stop here and let you think about whether C and D is a spanning set over the break. Okay, so let's take a 10-minute break.
This thing is going to be easier. Maybe we need to add an option.
Shit. Shit. Hello, let's go back, and yeah, we have a bit of technical difficulty, but anyway, let's back to our spanning set. Okay, so question C. So is this 101 and 010 a spanning set of R3? If you think it is a spanning set, raise your hand. And if you think it is another spanning set, raise your hand. Yeah, so that's correct. This is another spanning set, and it's because if you write it as if you write try to write some ABC of the alpha 1 times this 101 plus alpha 2 times 010, then we see that the linear combination here, the first dimension and the third dimension must both be in alpha 1 here, and yeah, and then because this must be the same, but A and C can be arbitrary. So when A not equal to C, then it's not in span of this 101 and 010. So C is not a spanning set. And now let's back to this very complicated D part. So do you think this is a spanning set or not? I guess this is no easy way to see this, but let's still take a vote. Do you think it is a spanning set? If you think it is a spanning set, raise your hand. And you think another spanning set, raise your hand. Oh, a lot of people see it's not a spanning set because you guys do rehearsal or do calculation. Okay, and indeed this is another spanning set. Okay. And to see it's not spanning set, we need to do virtual calculation here. So we have ABC equal to this alpha V1 plus alpha 1 V1 plus alpha 2 V2, alpha 3 V3, and then we write this out and equate two sides. Then we see that we have this linear system equation for alpha 1, alpha 2, alpha 3. So basically you have those three columns, this integral as a matrix. Okay. And yeah, so we solve this linear system of equations. So we have this matrix with those 3 columns, and that should equal to ABC. So we have our augmenting matrix. So this matrix with ABC, and then as usual, we solve this by our Gaussian elimination. So we go to make this right left-hand side REF. And we see that the last column has this 0, 0, 0, and it should equal to something. Okay. And this something is, it's really arbitrary. It's some function with ABC, and on some ABC this is not 0, then we have 0 equal to not 0 cannot be satisfied. Okay. So this system is inconsistent when we have this 2a minus 3c plus 5b not equal to 0. And yeah, so we have this condition, then we cannot find alpha 1, alpha 2, alpha 3 to satisfy this equation. And that means alpha 2, alpha 3, alpha 1, alpha 2, alpha 3 doesn't span vectors with satisfy this thing. So D is not a spanning set for R3. Okay, question? And yeah, let's go back to see a very interesting theorem that we can have for this use this idea of null subspace. Okay, so we have theorem 3.2.2 that says that tells us about the solution for A is equal to B when there are infinitely many solutions. Okay. So if we have A is equal to B is consistent, and yeah, so consistent means that it has one or infinitely many solution, and well, if it's a unique solution, then it's a unique solution. But if we have infinitely many solution, then there is a nice way to describe it. Okay, so the way to do it is first you find whatever solution, so the x0 called a particular solution. And so every other solution can be written in this form. So I guess here I should be boldface. Good. So any vector y will be a solution if only if it can be written as it should be boldface y. So it can be written as y equal to x0 plus z. And what's z? Z is something funny. So z is not a solution to x plus a is equal to b. Z is actually a solution to AZ equal to 0. Okay, so A is equal to 0. Okay, so Z is the null space of A. Okay. And this is a very important concept, and this is why we told. Basically, this theorem is why we spend a lot of time talking about homogeneous solutions. Homogeneous system AZ equal to 0. Because this will tell us, because we see this AZ equal to 0, so solution set will actually tell us a lot about A is equal to B solution set, where B is arbitrary. Okay. And yeah, so this is so important. We have a whole bunch of names here. So we have X is 0 called the particular solution, and this Z is called the homogeneous solution because it's a solution to this homogeneous system. And a particular solution just because it's one particular solution to A is equal to B. And yeah, we don't have a full proof of this theorem. I guess the proof is not too hard, and we only prove it in one direction. So we prove the if direction. So if y equal to x0 plus z, we prove that ay equal to 0. So you can just write it out. So ay equal to a times x0 plus z. And ax0 equal to b, and az equal to 0, and you have b plus 0 back to b. And yeah, hopefully from here you see we want az equal to 0, because if instead you have az equal to b, then you have b plus b equal to 2b, and that doesn't work out. Okay. So you want az equal to 0, so you add another 0 here, and you go back to b. So here, the important thing here is you want to be adding 0 here. Okay. And the other direction are not too hard. You can also prove it. Yeah. And but yeah, it's important to remember this theorem to us about the structure of Ax plus b, X is equal to b. And in particular, I guess important concept here is you see that so we have talked about N of A is a subspace. Okay, so this null space of A is the subspace of your Rn vectors. Okay, but A is equal to B, the solution is not subspace because it can look like something like this. So here we have an example where I guess X is three-dimensional, so we can draw everything in three-dimensional space, and also we have an example where null space of A is two-dimensional. Okay, and anyway, so N of A is a subspace, but the solution set of A is equal to B is another subspace. Okay, so nice thing to know here is that this is another subspace. Okay, usually. In general, there are another subspace, but it's a subspace that being shifted by some amount. So you see that everything inside S is, I guess we didn't quite prove it, but you can see that everything inside S is just everything inside A shifted by this particular solution. Okay. So yeah, this is theorem 3.2.2. I guess in particular you see that S is not subspace here when x0 is not 0 because 0 is not inside S. Okay. For the set to be a subspace, you want 0 to be inside S. So 0 is not in S in general. I guess that's right in general here also. In general. Okay. Any question? If not, then that's this end of this subsurface section. So a bit of a review. We have the definition of a subspace. So we have subspace is is a subset of a vector space V when that is closed under operations of V. So closed under addition and scalar multiplication of V. And we will talk about two subspaces here. First is the null space of A. So the null space is the solution set to A is equal to 0. Okay. And we have a theorem saying that solution to A is equal to B is a particular solution plus a homogeneous solution to A is equal to 0. And then we talk about the span of the vectors is the set of all possible linear combination of vectors. Okay. And then we also talk about the spanning set of a vector space. Okay. And yeah, so we have as I said, we have we have let's try to draw a little bit here. So we have a set of vectors vi and maybe wi, and they can span. Let's try to write here. So a set of vectors can span to let me think about how do I write this direction. So maybe let's write so they all connect to some subspace W. Okay, and so this direction is called span. So you can take all linear combination of your set of vectors and they become you become span, and they can be W, and then for W you can find the spanning set. Okay. W can have a whole bunch of spanning set. Okay, and yeah, so that's 3.2. Any question? And if there is no question, then yeah, let's go into deeper about this idea of spanning set. So as we said, we have a vector space W. Yeah, I should keep say W here. Okay. So we have some W that's a span. Then there are there are many different set of vectors that can span your whole W. And in particular, sometimes you might have redundant things, redundant vectors in your span. I guess we already see this. Let's try to jump back, and hopefully it's okay. Okay. No, too little here. Here, yeah. So we see in our first example A here, we only need A1, this E1, E2, E3 to span our whole R3. And yeah, so this 1, 2, 3 here is redundant. Even if we don't have this 1, 2, 3, we still span the whole R3. Yeah. And yeah, so now our idea is we want to find some good spanning set for our vector space W. So our vector space W has a whole bunch of spanning set. And in particular, we want some smaller spanning set. So first thing we want to do is we want to find a minimal spanning set. So if you have a whole bunch of vector, but if we can span our space W without some vector here, then yeah, then then maybe we can we can just have a smaller set, and well, smaller set is better because there are less things to write down. Okay, yeah. So we want to find this minimal spanning set. So minimal just means that you cannot remove anything here to still get the same space that you span. Okay, and yeah, and so okay, so we now want to find minimum spanning set, and then it turns out to find a minimum spanning set, you need to find this relation of how the vectors in our this generating set. So generating set is just this V1 to Vn, how they linearly depend on each other. Okay. So this is a bit of a spoiler. Okay, so we are going to find how vectors depend on each other and our fate whether they are a minimal spanning set. And the key idea here is minimal, means that you cannot remove anything and still get the same set here. Okay, and yeah, let's see some example. And it's a more complicated example. So we have x1, x2, x3 here. These three vector, and it span something, some s, and inside R3 span by them. Okay, so we have, but then here we see that we have this dependency relationship here, and we didn't show that how we calculate it, but we just say it's true. So actually, 3x1 plus 2x2 will equal to x3. Okay, so we have this. Dependency relationship here, 3x1 plus 2x2 equal to x3. And because of this dependency relation, we see that we don't need x3 in our spanning set x1, x2, x3. Because any linear combination of x1, x2, x3 can be just written as a linear combination of x1, x2. So say we have this alpha 1, alpha 2, alpha 3 here, linear combination. Then this alpha 3 x3 can be written as alpha 3, 3x1 plus alpha 3, 2x2, okay? And yeah, so you move things around, then you see this alpha 1 plus 3 alpha 3x1 plus alpha 2, 2 alpha 3x2. So any linear combination of alpha 1, alpha 2. Alpha 3 can be just written as a linear combination with some other alpha 1 and some other alpha 2, okay? So span of x1, x2, x3 just equal to span of x1, x2. Okay. And yeah, so you have this linear dependence, then so I guess here I should write linearly here. So linearly. Okay, linearly depend on each other. If you have a linear dependence, then we can get rid of a vector in our spanning set. Okay. And then we can also rewrite this in better form. So this 3x1 plus 2x2 equal to x3. we can move everything to the right hand side to make it look a little nicer. So we have 3x1 plus 2x2 minus 1x3 equal to 0. Okay. And yeah, so we see that this x1, x2, x3 is not a minimal spanning set because we have this dependency relation. So it has 3x1 plus 2x2 minus x3 equal to 0. Okay. And indeed, from this relationship, we also see that this span can be equal to any two span because we can also write x1 as a combination of x2 and x3, or x2 as linear combination of x1 and x3, etc. etc. Okay. And yeah, in general, let's go to think about yeah, let's do, I guess it's a bit annoying. Anyway, yeah, so now let's forget about this example. So this is the end of the example. But let's just see, in general, if we have just any two vector in x1, x2. So I guess example 1 ended. I should say ex1 ended. So in particular, in general, so here is in general, so now we just have arbitrary x1 and x2, and let's satisfy c1 x1 plus c2 x2 equals 0 for some non-zero c1 and c2. Then you can either write as c1 as some number times c2, or x2 as some number times c1. So if c1 not equal to 0, you can write this, and c2 not equal to 0, you can write this. And oh, sorry, yeah, so sorry, I got confused. So let's so this is actually still in ex1. Sorry, I got confused myself a little. Okay, so here we want to prove that x1, x2 is already in a minimal spanning set. Okay, and this is really weird logic. So still in ex1. Logic here is a bit confusing. Okay, so I guess yeah, let's do this once again. So let's see high level. So we have this x1, x2, x3 here, and yeah, we say that x3 has this dependency on x1, x2. So we can eliminate x3, and we know the span of x1, x2, x3 is just span of x1 and x2. Okay, and yeah. And then we want to see kind of the other direction. And here we already see, I guess we can already see x1, x2 is already minimal because so let's say this first. So x1, x2 is minimal because can write x1 as x2 as c as because we cannot write x1 as something times x2 or x2 as cx1. Okay, so wherever you have a linear combination of x1 and x2, you cannot write the x1 part as x2 or x2 part as x1. Okay. And so yeah, so it's this equation here, this writing here. So we already have this is minimal. Okay, and then we kind of prove this in the other direction, then we already know this is minimal, and we have observation here that if this is minimal, then we cannot find C1x2, C1x1 plus C2x2 equals 0 with non-zero x1, x2. Yeah. And then here is the proof. So if you have not both 0, then we can write either x1 equal to this non-zero times as something times x2, or if c2 is not 0, we can write x2 as something times x1. But we know none of those happen, and none of this is true. So this only happens when c1 equals to c2, when c1 equals to c2 equals to 0. Okay, and yeah, so I guess really we want the theorem is this thing. Okay, and so in the book it's just write down these two conditions, but I think this is really should be a theorem, so let's call this theorem 3.3.0. So it has two parts, and we actually get proof. So first is that you have a whole bunch of vector and span some vector space V. So it's really annoying, but this really should be a subspace of a larger space. Anyway, so it spans some vector space V, and if one vector of them can be written as a linear combination of other vectors, then we don't need this vector. You can just use other vector to span V. Okay. And also the second one, we says that we have a whole bunch of vector. So yeah, and so really we have three things. So we have whether we can remove one vectors. So the first is the condition one says that can remove one, can remove one V, and so condition one says that if V equal to LC of other. Okay, so condition one says if there is some V that's a linear combination of other vector, then you can remove V. Okay, and remove some V. Okay. And then condition 2 talks about this V is a linear combination of others. Okay. I guess it's a bit more harder. So a bit different. Okay. So the condition 1 says it exists, and the condition 1 is only exists 1, okay, and yeah, I guess it doesn't matter so much, so let's be a bit lazy about quantifier. Okay, so yeah, so here we say if some V is a linear combination of others, then you can remove that V. Okay, can remove that V. And condition 2 says that so let's do exists V equal to LC of others. So this condition here, and here is if only if we have now this dependency relation that we are going to talk a lot today, a lot in this chapter. So this is the most important equation. So if only if this some Ci Vi equal to 0. Okay. Has a non-trivial solution. Okay, and non-trivial solution means a solution that's all 0. So, and by solution we means we pick C1, C2 to Cn. Okay, and obviously if you pick all the C here equal to 0, then you have a whole bunch of 0 vector, and together it's still the 0 vector. Okay, and so yeah, and so here the thing we want to determine is whether this thing has not all 0 solution, which is also called a non-trivial solution. Okay, so we want to see whether C1 this equation has a non-trivial solution, and that will mean whether there is some V that's a linear combination of others. Okay, and yeah, and then that will also means that so whenever you have a non-trivial solution, this is not quite complete, but well, yeah. So whenever you have this thing, so if you have a dependency, so you have a non-trivial solution of this thing, then you know that there is some V that can be written as a linear combination of others, and then you know our set is not a minimal spanning set because you can remove that V from your vector space V, the small v from your vector space V. Okay, so that's kind of idea, and let's see proof. Okay, so proof of 1. So if there is a V that can be written as a linear combination of others, so V is some beta to other V's. Okay, and then we have then we want to say this V1 to Vn-1 can span the whole space. Okay, so we need to write any space in this V can be written as a linear combination of V1 to Vn-1. So let's say this V is written as alpha 1 to alpha n with this V1 times this V1 to Vn adding together. And we want to replace this alpha n Vn to some other to linear combination of V1 to Vn-1, and we can just use this equation. So Vn is beta 1 to beta n-1 with V1 to Vn-1, and then we move things around. So you see this is just alpha 1 plus alpha n beta 1 times V1, and alpha 2 plus alpha n beta 2 V2, etc. So you see this is a linear combination of just V1 to Vn-1, and with different coefficients. So we see this alpha n coefficient can be just multiplied on these beta coefficients and add back to those alpha coefficients. Okay, so this complete proof of 1. So if there is any vector in V that can be written as a linear combination of V1 to Vn. So any vector in V can be just written as a linear combination of V1 to Vn. So V is just span over V1 to Vn. I guess V1 to Vn-1. So important to have Vn-1. Okay. Yeah. So this is proof of 1. If you have a linear dependence, then you can remove 1V. Okay. Yeah. I guess here we didn't prove the other direction, but it's what it is. Yeah. So you have a linear dependence, you can remove 1, and then proof of 2. Okay. And proof of 2, then proof of 2 is actually a if only if condition. So we want to say you have this dependency relation that has a non-trivial solution. Then one of them actually can be written as a linear combination of others. And it's quite straightforward, but the writing is hard. Okay, so first one, the only if direction is easy. So if one of them can be written as a linear combination of others. So without losing the generality, let's once again assume it's a Vn. So Vn is this linear combination, alpha linear combination. And we can just move all those things back to the left hand side. So I guess I move this to the right hand side and switch left and right. And we have this just alpha 1 v1 all the way to alpha n minus 1 vn minus 1 and minus vn equal to 0. Okay. And yeah, so this is indeed equation of this C1 to Cn form. We just have Cn equal to minus 1. Okay. And we see this as a non-trivial solution because Cn equal to minus 1. So even if all those alpha equal to 0, Cn equal to minus 1 is non-zero. So this thing is non-zero. So we have non-zero, not all zero solution. Okay. And and then we go other way around. So we have this some C1 to Cn, Cn equal to 0 with some Cn equal to 0. And without losing of generality, let's this non-zero Ci we assume is Cn. Okay. Okay, let's assume this is Cn. Then we can divide everything by Cn because it's non-zero. So we divide everything by Cn, and then we have a coefficient of 1 in front of V, and we just move everything to the other side. We see V is Vn equal to this minus C1 divided by Cn V1 plus minus C2 divided by Cn V2, etc. So we have Vn equal to whole bunch of coefficient times V1 to Vn. And those coefficients might be 0, non-zero, doesn't matter, we have Vn multiplying on 1 here. Okay. So this is a proof of the second part. Okay. So this okay, so here is a summary again. We have two things. So first, if you have one thing that can be written as a linear combination of others, then you can remove that one. And also one thing can be written as a linear combination of others if only if you have a non-trivial solution to this linear combination equation. Okay. And yeah, so this equation is so important that we also give it a name. Okay. And the name is the title of the chapter is called linear independence. Okay. So so a set of vector is linear independent if only if that this equation only have a non-trivial solution. Okay, and it is so important we have a name for both sides of this property. So it has a linear independent, and a linear dependent. So those are the linear dependent and the linear independent are just negation to each other. So linear independent if this equation only have a non-trivial solution. And the linear dependent is the reverse of this thing. So this equation has a non-trivial solution. Okay. So exists not all zero solution. Okay. So very important here, not all zero. And yeah, also note here. So you have a set of vector, then you always have a trivial solution. So you cannot just say it has a solution because this equation always a solution that's all zero. Okay. And then let's do a bit of a spoiler. Okay. I guess the proof we didn't. Yeah, we will talk about this in more detail later because I only have 5 minutes. So it's a bit of a spoiler to next section. So it's an idea called basis. Okay, so basis is a spanning set that's minimal, and also we'll prove that it's minimal if only if all of them are linear independent. And we kind of proved this in 3.3.0, but yeah, but we didn't quite prove whole because because we only have one direction here, so we need to have another direction here to make the proof of basis being a bit more complete, but that's partially. So here this is partially because we only have one direction on the part 1. And anyway, we'll come back to this later. But the thing we want to talk more about is things about this idea of linear independent here. Okay, so here is the idea or is the definition of linear independent, and I want to just show a bit intuition of this thing. Okay, so we have some example of a linear independent. So we have two vectors. So this 1, 1 and 1, 2 are linear independent because you want any C1, C2 on them equals 0, equals 0. And yeah, we have E1, E2, E3, and these X are they linear independent or not? And this example is from previous example, and we already see X3 can be written as a linear combination of 1, 2, 3, and they are linear dependent. And yeah, let's go back to the example later, and in the next minute, I want to show this geometric interpretation of the linear dependent. Okay, so you have just two vectors in R2, then two things are linear dependent if they are on the same line. Okay, so you have this x1, x2, and y1, y2. They are linear dependent, and that kind of means they are on the same line. And they are linear independent if they are not on the same line. And then you see that they span this whole two-dimensional space. Okay. And then if we are in three-dimensional, you have two vector, and linear dependent kind of means this. So you have x1, x2, and they already span the space. And then linear dependence of z on x1, x2, z on xy means that z is in the span of x and y. So all three of them are in the same two-dimensional space. And but if you have your z that's outside of this plane, this plane spanned by x and y, then they will be linearly independent. And so yeah, here is a bit of a geometric intuition about linear dependence, and we'll talk about more properties of linear independence on Wednesday. Okay, yeah. So sorry, we actually have 10 more minutes, right? Sorry. But anyway, I guess it's a good starting point here. So yeah, let's start 10 minutes earlier today. So yeah. See you on Wednesday. Yeah.